Welcome to Unit 5 on sampling distributions. In today's video, we're going to focus on topic 5.6, sampling distributions for the difference in sample proportions. So we just got done looking at a sampling distribution for a sample proportion, right? So we knew the true proportion, and we were trying to determine what could all possible p-hats look like. Well, we're going to do something very, very, very similar to that in this video, but we're not going to look at one population's proportion. We're going to look at the difference between two population proportions. So here's what I'm talking about. One thing many research studies aim to do is to see if there's a difference between two different population proportions. For example, a teacher might wonder, is there a difference between the proportion of boys that do all their homework and girls that do all their homework every night? So we have two different populations, boys and girls, and we want to know, hey, what's the difference between the proportions from each? Another example could be an economist might wonder, is there a difference in the proportion of unemployed adults in the United States and the proportion of unemployed adults in Canada? So again, we got two different populations, adults in the US, adults in Canada, and we want to know, is there a difference in the proportion of unemployed adults in each population? A third example is a marine biologist might wonder, is there a difference between the proportion of diseased coral reef in the Atlantic Ocean and the proportion of diseased coral reef in the Pacific Ocean? Again, two different populations, coral reef in the Atlantic, coral reef in the Pacific, and we want to know, is there a difference? So again, what we just got done doing in the previous topic was looking at one population and wondering something about that one population. Well, now we're wondering about the difference between two. And remember, anytime you look at two different things, you want to compare them. And when you compare them, you look at the difference. So this is going to sound very familiar, right? All of these types of questions can be answered if we start out by looking at a difference between two samples, one drawn from each population. But remember, one difference between two samples doesn't really tell us a whole lot. All right, so let me just kind of give you an example of this, right? Let's just say we get a proportion of girls, and it comes back that 50% do their homework, and we get a proportion of boys, and it comes back that 45% do their homework. Okay, that's a 5% difference. But that doesn't mean the true difference is 5%. I mean, the truth could be bigger, smaller. It could even be negative, right? I mean, these two samples show that girls do their homework more often than boys, but it might be true that boys do their homework more often than girls. I mean, this is the problem, right? Samples vary. So just looking at two samples alone and looking at the difference between them doesn't really tell me a whole lot. What I need to do is build a sampling distribution. Because remember, a sampling distribution for the difference will show me what all possible sample differences could be. My single difference in this example here is 0.05, but that's just one possible difference that exists between these two samples. I need to think about what all possible differences could look like. And of course, that's a sampling distribution. So we need to build a sampling distribution for the difference between two sample proportions taken from two different populations. And what's completely crazy is that we saw this in the last topic as well, is that we're going to be able to build one of these sampling distributions without actually looking at any samples. All right, before we begin the process, I do have to be very clear here that there's going to be a lot more numbers in these problems because now we have two different populations, okay? So generically, we could label them 1 and 2. So we got population 1, population 2. Now, population 1 is going to have a true proportion of P1. This would be the true proportion of girls that do their homework. So again, in an actual problem, you're probably not going to use 1s and 2s. You're probably going to use some type of abbreviation. So you could even say, hey, the truth is, maybe I read in some education manual or education newsletter, the true proportion of girls, take that back. I put a hat on there. It should not have been a hat. The true proportion of girls that do their homework is 65%. Okay, great. So again, I'm using a G for girls because that's what you would do in an actual problem. But again, we've got to just be using 1s and 2s to kind of be general here. So then when it comes to the boys, right, the true proportion of the boys, maybe again I read this in some education journal, the true proportion of boys that do their homework is 0.61. Okay, so the idea here is that you're going to have a true proportion from the first population and a true proportion from the second population. Then a sampling distribution looks at all possible samples that could come from that population. So for me, that would be all potential samples from girls, all potential samples from boys. So 1 and 2 is being general, but again, in your specific problem, you're going to use some type of abbreviation for the actual context of your problem. Now, here's something else that's important, is that the sample sizes do not have to be the same. I can look at a sample of girls and a sample of boys, and they don't have to be the same. That's the fairness of proportions, right? The whole reason why we use proportions to compare two things is because, let's just say we looked at 200 boys and 125 girls, or vice versa, that, you know what, it's okay, right? It's as long as we're looking at the proportion of that sample that did their homework, then the fact that one sample is bigger or smaller than the other doesn't really matter so much. All right, so let's just say that we're going to look at a sample of 200 girls and a sample of 125 boys. The idea here is that the p-hats that could potentially come up from the girls sample, I mean, who knows? Yeah, I expect 65%, but I could get something higher, could get something lower. Same thing could be said from the boys. Yes, for the boys, should be 61% that do their homework, but, you know, samples vary. Sample could come back higher, sample could come back lower. All right, so now let's dive into what needs to be done to build the sampling distribution. All right, first we need a center, right? The center is literally the mean of all the possible differences. So if we think of all the possible differences that exist out there between a sample of girls and a sample of boys, the mean would be the truth, the true difference between these two populations, right? Now, there is a condition attached to this, and this should sound familiar. Both samples have to be random to avoid being biased. Now, in the previous problems, we only had one sample. Well, now we got two, so we just got to make sure we add that word both in there. So again, if I'm talking more specifically about my sample, I'm going to say, hey, listen, the true difference between girls and boys, right? Now, again, if you're looking at p-hats, a p-hat of girls, a p-hat of boys, who knows what you could get, right? I mean, the difference could be anything. But we know that it should be about 4%. Because girls, again, I read 65%, boys 61%. So the difference should be 4%. Now, you could reverse that difference and get negative 4%. It actually does not matter, but I prefer to always look at a lens through, look at these problems through a positive lens. So I always will do it in the order that creates a positive number. But it's important that you just know that girls should be 4% more than boys. So at the end of the day, yes, we are looking at two different samples. We are looking at two different populations. We are comparing two different proportions. All that's true. But remember, when you compare, all you focus on is the difference. So all I really care about is that the fact that there should be a 4% difference. Now again, the boy sample could go up or down. The girl sample could go up or down. So I might get a bigger difference, or I might even get a smaller difference. And that's totally okay. The center is simply what you expect. All right. Now, of course, there's a standard deviation involved as well. This is the spread. This will tell us how those differences could spread, how those differences could vary. Sometimes the differences could be higher. Sometimes the differences could be lower. So we have a formula here. Now, real quick, we got to go over that condition one more time. The samples have to be independent of each other's. So I'm talking about all of them, right? I'm talking about both samples. So I'm talking about within the boys, there's tons of samples, right? Possible samples. They have to all be independent. Same thing with the girls. Now, the formula here is it's a little bit tricky looking, but it's really not too bad. What it boils down to is it's a giant square root. We have P1 times 1 minus P1. Remember, you're never actually going to do the 1 minus. I mean, you're going to do it, but usually you're just going to do it in your head. It's just the opposite. So if 61% of girls do their homework, then 39% don't, okay? And then divide it by the sample size. And then for the boys over here, you'd have the P2, the proportion of the boys, that'd be the 60, excuse me, I said that wrong. The girls were 65%, and the girls that do not do their homework would be 35%. The boys were 61%, and then the not doing their homework for the boys would be 39% divided by their sample size. Now, this is, first off, if you just look at half of this formula, like if you just go right down here, this is what the formula was in the last topic for a single proportion. So all we're doing is adding in the second one. But I want to make sure everybody understands where this formula comes from real quick. If we're thinking about the standard deviation for the girls, right? Just the girls, okay? we're doing 0.61 times 0.39 divided by 200 girls. Okay, that's what we literally just learned. And then the standard deviation for a sample of boys would be 0.6. Oh my gosh, I did it wrong again. I'm so sorry. And actually, this is, I'm literally not doing this on purpose, but this is important because it is very confusing to get some of these numbers confused. So make sure you're really kind of looking at what's given to you and keeping it organized. So for the girls, remember 65%. So the not doing the homework girls would be 35%. For the boys, it was 61%. The one minus that, not doing their homework, would be the 39%. And then there were 125 boys. So again, these are the standard deviations for each. Now what I need to do is combine these two standard deviations together, because what I'm doing is I'm looking at them together, right? I'm looking at their difference. So remember the rules of combining standard deviation. You're not allowed to add standard deviation, but you are allowed to add variance. So to find the variance, all I have to do is square the standard deviation. So I'm going to square the standard deviation. Again, to find the variance for the boys, square the standard deviation. So I'm just going to square the standard deviation. Now something really cool happens is that the square roots cancel. So I get 0.65 times 0.35 divided by 200 for the girls. That's their variance. So the inside without the square root is the variance. And then I got for the boys, the variance is 0.61 times 0.39 divided by 125. Now remember, even though we're looking at the difference, one of the other rules we learned is that standard deviation variance always builds. So you're never going to subtract standard deviation. You're never going to subtract variance. It always builds together, even when you're focusing on the difference. So now that I'm adding the variance for the girls, the variance for the boys, now I need a giant square root around all that to get the standard deviation for the difference. So again, this is the standard deviation for the difference between a sample of girls and a sample of boys. All right, and this is actually really easy to type into your calculator. Don't do it in pieces. I mean, you can, but a lot of kids do something wrong when they try to do it in pieces. I recommend just typing it in straight on your calculator. So start with the square root, then go 0.65 times 0.35 divided by 200 plus 0.61 times 0.39 divided by 125, and you get 0.0551. So that's about, about 5%, about 6%, whatever, almost right in the middle, between 5 and 6% that we're going to vary by here, okay? So it's not too bad of a formula, and I just want to make sure everybody understands exactly where it comes from. It comes from following the rules of combining standard deviation that we've talked about in the past. All right, so now keep in mind independence. Let's talk about independence one more time here. To be honest, to truly have independence in your samples, you need to sample with replacement. So if you take out 125 boys, you need to put them back before you take out that next sample. Because remember, sampling distributions are repeatedly sampling. Well, in the real world, we're not really expected to sample with replacement. It's just not something that's feasible in the real world. So every time we take a sample out and we do not replace it, we're technically changing that population. And this is where that 10% rule comes in. We say, you know what, that slight change, if we do not replace, is negligible. It's totally okay. It's not a big enough change for us to be concerned with, as long as both of our samples are under 10% of their populations. So for the girls, I'm definitely going to assume 125 girls is under 10% of all of them. So I'm safe to say that, taking out 200 girls is not going to make a negligible difference, or will make a negligible difference, one that's not really concerning to me. And same thing for the boys, right? I do need to make sure both samples are independent of each other. All right, and then finally, let's talk about sample size one more time. I mentioned this in the last topic. I just need to keep, saying this. Bigger samples vary less, bigger samples vary less, bigger samples vary less. This applies to looking at the differences too. The standard deviation for the difference between two samples will vary less if those two samples are bigger and bigger and bigger. Because the bigger your samples are, the closer they will be to the truth, which means your difference will be closer to the true difference as well. All right, the third item that we need to create our sampling distribution is, of course, the shape. The shape of the sampling distribution is going to be normal, provided that both samples are sufficiently large. Now, what does that mean? We talked about this in the last topic as well. It means that both samples are 10 or more successes. Both samples have 10 or more failures. You got to make sure that you have enough in your sample to be big enough, right? And what that means is you need every sample to have 10 or more successes. So I need 10 or more girls and 10 or more boys that do their homework every night. And I also need 10 or more boys and 10 or more girls that do not do their homework every night. So you actually have to go ahead and show the work for this, right? It's not that difficult. You would just take your 200 girls times it by the 65% that do their homework, take your 200 girls, times it by the 35% that do not do their homework, check that both those numbers are bigger than 10, and then repeat this for the boys, 61% and 39%. So make sure all of those numbers, and again, even though it's obvious, even though like, yeah, I know, I don't need to figure it out, I just know from looking at numbers that they're going to be bigger than 10, you still need to check that work and make sure you actually do it, okay? Now remember, this allows us to build our normal model. So we know that, here's that normal model. We all love that normal model. Sorry for my very crappy drawing here. But the idea is in the middle is the 4% that we expect. We expect a 4% difference between girls and boys that do their homework, right? So that's the center. If you were to take a look at sample of girls, sample of boys, sample of girls, sample of boys, many samples of girls, many samples of boys, on average, the difference between those samples is going to be 4% because that's what's true. But because we have a standard deviation, I'm just going to round the standard deviation to 5% for sake of making this picture. That'd go up to potentially 0.09, 0.14, even as high as 0.19. Now that would be pretty significant to be 3 standard deviations above. But again, this allows us to kind of see, what kind of differences could we expect. 9% might seem pretty big, but that would actually be kind of a normal difference to see, even when there's really only 4% difference. Now, when we go down, we're going to subtract. So it gives us to negative 0.01, negative 0.06, and then negative 0.11. So here, we're understanding that what's negative, right? What a negative? Let's take a pause for a second. In the previous topic, when we were looking at a single proportion, you can't have negative proportions, right? If you're looking at the proportion of boys that do their homework, you could have maybe as high as 100%, you could have maybe as high as 0%, but you're never going to get a negative value for a single proportion. But when you're looking at the difference between two proportions, you certainly could get a negative because the order that you subtract matters. So remember, I did girls minus boys. Well, if the boys sample came back bigger, more percentage of the boys did their homework, because remember, these numbers are allowed to vary, then if the boys came back higher and the girls came back lower, then I could get a negative difference. So a negative difference would simply tell me that in those particular samples, the boys were bigger than the girls. More boys did their homework in those samples than other samples, okay? So we'll talk a little bit more about that in a moment. So here's kind of a summary of all this: mean, standard deviation, and the shape. Please make sure all conditions are checked. Unfortunately, now we have to check all the conditions twice because we got to make sure both samples are random. Both samples have to be under 10% of the populations to assume independence, and both samples have to be large enough with 10 or more successes and failures. So it's a little bit more work to check those conditions, but you definitely got to do it. So the idea here is now we can build a sampling distribution without taking a single sample. It's really crazy. All we need to know is the true population proportions, and we need those sample sizes, of course. So it's really easy, right? It's not that much different than what we just did. This allows us to see what all potential differences could be. Now, I do want to mention one more time this idea of 0. Why is 0 such an important number when you're looking at the difference between two things? Because if you're looking at the difference, and again, I'll use my example of looking at girls minus boys, or the proportion of girls in a sample versus the proportion of boys in a sample. And again, 0 is an important number, right? Because 0 is when they would be tied. I expect a 4% difference, but again, both of these numbers could vary. The proportion for boys could be higher or lower, same with the girls. So if the boys end up being higher in one particular sample versus a sample of girls, then you're going to get a negative difference. But 0 is the cutoff, right? 0 is what determines positive numbers to the right of it, negative numbers to the left of it. So oftentimes we're going to talk about, when we're comparing, we're going to ask you about, hey, could the boys be bigger? Could the girls be bigger? What's the probability that the boys are bigger? What's the probability that the girls are bigger? Well, again, that comes down to really focusing on 0, because 0 is that cutoff between, on the right side, girls bigger, positive numbers. On the left side, boys bigger, negative numbers. So make sure you truly understand that. We have actually talked about that in the past, so it is coming up again. All right, guys, that's it for this video, this kind of video that discusses looking at the difference between two sample proportions. There is going to be a follow-up video to this that has an example to kind of walk you through an actual example of what this would all look like in a full-fledged example. I know I used my girls and boys example in this video, but stay tuned. If you need that extra video, please make sure you watch it. It'll definitely help you understand what this video was explaining to you. All right, see you in the next video.